Okay, so here we have section B, where it's more long answer. A lot of sections depend on each other, and I'll try to squeeze my handwriting in as much as I can, but we'll see how it goes. So, first one, we've got a function, and it is asking us to do the derivative, and we actually know what the answer is supposed to be. So, let's just take the derivative. So, if I have a fraction, I have to use the quotient rule. Just for a reminder, the quotient rule, f prime g minus fg prime divided by g squared. F is the top and g is the bottom. So if I have the derivative here, I'm going to do the derivative of the natural log of 5x. That's f prime. So natural log of 5x is 1 over 5x times 5. So f prime times g, kx, minus f, natural log of 5x, times g prime, k, all divided by g squared, kx squared. Lots of nice stuff cancels out here. 5 cancels with 5, x cancels with x. So what do I really have on top? I just have k minus k times the natural log of 5x. And on the bottom, I'm going to square k and square x. You might notice that the top has a k in common, so you can factor out a k. It's leaving you with 1 minus natural log of 5x divided by k squared x squared. And you can cancel one of those k's out, and you have the desired result. It's really nice on this type of problem because you know what you're trying to get to. And so I knew that I needed to be able to cancel out one of the k values from the top. And so I was looking for, where are my common terms, how can I factor, and how can I cancel? Next, on part B, it says the graph has exactly one maximum point P. So we need to find the x-coordinate of P. You're going to find a maximum or a minimum by setting the derivative equal to 0. And so we're going to take our first derivative, 1 minus natural log of 5x over kx squared, set it equal to 0. Multiply both sides by kx squared, and you don't have a fraction anymore. 1 minus natural log of 5x equals 0. Add the natural log, then exponentiate both sides. So e equals 5x, and then you have 1/5 e. Normally, I would need to go to the next step and prove that this is actually a maximum. But because the question told me there is exactly one maximum point, and I found exactly one critical point, I'm okay at this point assuming that 1/5 e is actually the critical point. So 1/5 e is our p value. Or you can write e divided by 5, whatever you want. Then question C, we talk about the second derivative. I guess we do not need to actually show that that is it. It just says, here it goes. Here's the second derivative. And again, it says 1 point of inflection Q. And so let's do the same sort of thing. Point of inflection is where the second derivative equals 0. So I'm just writing the second derivative equals 0. Just like before, we can multiply by the denominator and get rid of it. Just like before, we want to separate our terms. So add 3 to both sides. Divide both sides by 2. Exponentiate both sides. So you have 5x equals e to the 3 halves. Divide both sides by 5. And then you have the desired result right there. So 1/5 e is the maximum value. Okay, so the webcam disappeared. That's okay. So what we've got now is we've got our P and our Q. So let's scroll down and look at what's going on here. The region R is enclosed by F, the x-axis, and the vertical lines through P and Q. So we're going to find the area. That sounds like an integration problem. So let me just copy down the function one more time, ln of 5x over kx. So that's our function, f of x, natural log of 5x over kx. P was 1/5 e, and q is 1/5 e to the 3 halves. Double check on that. Looks good to me. Okay. So we're doing the integral from P to Q. There we go. Of f of x dx. And it even tells us the area is equal to 3. So when we set that up, we have 1/5 e to 1/5 e to the 3 halves, natural log of 5x over kx dx, and that's going to equal 3. So what I'm going to do is do a substitution here, because if I do a u substitution for the natural log of 5x, I can see its derivative, 1 over x, is in the integral here. So let's do a u substitution. U is natural log of 5x. That tells me that du is 1 over 5x times 5 dx. The 5's cancel out, and you get dx is equal to x du. The other thing I would suggest doing is redoing your bounds of integration. So if I plug in 1/5 e, that's an x value, my first u, my lower bound, is going to be the natural log of 5 times 1/5 e, and that just becomes 1, because the natural log of e is 1. And then u2, similarly, is the natural log of 5 times 1/5 e to the 3 halves. Sorry, can't quite fit it in there. And that all cancels out to just be 3 halves. It's nice to do your bounds of integration at this time so you don't have to worry about it at the end. So I'm going to slide over here. I have my bounds of integration from 1 to 1.5. I have u divided by kx, and dx is equal to x du. The x's can cancel out, and k is a constant, so I can change this to being 1 over k times the integral from 1 to 3 halves of u du. 1 over k, and that is u squared over 2, evaluated from 1 to 3 halves, which is 1 over k, times, I guess we can pull the 2 out as well, so 1 over 2k, and then we have 3 halves squared, so 9/4, minus 1 squared, which is 1. And I'll try to fit one more line of work here. 1 over 2k, 9/4 minus 1 is 5/4. So we have 5 over 8k. 5 over 8k. I'm going to clear the screen here. 5 over 8k is what we got from our integral, and we were told that the area is 3. So if I multiply by k, I have 5/8 equals 3k. And if I divide by 3, I have k equals 5 over 24. So a lot of different steps on this problem. Please feel free to ask for more explanation on any of those steps. Thank you.